Am I audible now? Okay, thank you, Oshan. Right. We still have only 80 participants, but we should have 160 some students. So that means we only have half of the class present even now. Anyway, let me begin the discussion. So we are in the middle of discussing limits and continuity. Limit of a function at a point is how the function behaves near that point, not exactly at the point. What happened to the function as the independent variable approach to that point. So we looked at what happened as the independent variable approach to that point from two sides, um, from the left hand side and right hand side separately. We call those one-sided limits, and if the one-sided limits are equal, we have the two-sided limit. And um, last time means yesterday, we saw what happens uh, if the two-sided limits are different, and what happens if the two-sided limit, uh, so if the two-sided limit is different from the function value. So in those cases, we have a discontinuity in the graph. One-sided limits are different. We have something called the jump discontinuity because there is a gap between endpoints. On the other hand, if the one-sided limits are equal and the function value is different, that means there is a gap between the function value at that point in the graph. It is, let me show you a picture. Pictures are, yeah, you can see it from this, the leftmost picture. So we have a hole on the graph and the function values is in somewhere else. This is called a pole discontinuity or a removable discontinuity. So jump discontinuities, removable discontinuities, and sometimes we have these infinite discontinuities. The function value uh, goes to plus infinity or minus infinity. Or sometimes they go, one part piece goes to the plus infinity and the other piece goes to minus infinity. Sometimes both of them can go to plus infinity. I think I have not given you an example for that. Let me give you one example. Now you should see them. All right. Now you should see my notepad. So, yeah, 1 over x. The domain of this function is every real number except 0. So, for this graph, for the graph of this function, we have an infinite discontinuity at the origin. At, at x equals 0. X equals 0 means the y-axis. So y-axis is a horizontal asymptote. So for this function, as x goes to 0 from the right hand side, means y value is plus infinity and as x goes to 0 from the left hand side, y values goes to minus infinity. This is the primary example for an infinite discontinuity. You should keep this in your mind all the time. So sometimes people say 1 over 0 is infinity. I've seen even uh, A-level students, even some university first year students say 1 over 0 is infinity. It is completely wrong. Depending on how you approach to 0, you get two different limits. But still function is undefined at 0. It has no value. Uh, Let me show you a variant of this example. Y equal 1 over x squared. So still x is different from 0. So what you do is you take some real number different from 0, square it. When you square it, you get a positive number. Then you take the reciprocal. So reciprocal of any positive number is again positive. So this results in a positive number always. No matter what you do, it gives you a positive number. So the graph of this function looks something like this. It still looks like a parabola. For positive x values, you get positive y values, and for negative y values, you still get positive. So for negative x values, you still get uh, positive y values. So the graph looks like this. So both one-sided limits actually equals to positive infinity. Both right limit and left limit are equal to positive infinity. But still, the function value, so the two-sided limit exists. The two-sided limit is infinity, positive infinity, because one-sided limits are equal. But the problem is function value is undefined. So if you take f of x to be 1 over x squared, then you cannot substitute 0 into this function. This is undefined. You cannot find the real number. For this reason, even though the two-sided limit exists, the function has no meaning at that point. For this reason, f is not continuous at x equals c. So it has a discontinuity at x equals 0. This is not a whole discontinuity or a jump discontinuity. This is an infinite discontinuity because the one-sided limits goes to infinity. Both one-sided limits goes to positive infinity, but because the limit is infinity, limit is not finite, we call it an infinite discontinuity. Do you have any questions? So we discussed these examples last time. This is best of last time. So do you have any questions from the last class? Anything, anything that you want to clarify? Any examples in particular? If not, let me tell you something about continuous functions. Examples for continuous functions. So I call these continuity theorems. But the one thing you need to understand is most of the functions that we know are continuous on their domain. Power functions. So that includes simple functions like x squared, x to the third power, x to the fourth power, x, 1 over x. 1 over x is also continuous on its domain. You saw that in that example, the problematic point is 0, but 0 is not in the domain of 1 over x. For every point in the domain, function 1 over x is continuous. So power functions are continuous. Then polynomial functions. Polynomial functions means combinations of powers like x squared plus 2x plus 3. That includes quadratic functions, cubic functions, all those things. Then rational functions. Rational function is a quotient of two polynomials. As long as the denominator is non-zero, function is well defined. So for all the points except the zeros of the denominator, rational functions are continuous. We did not talk about trigonometric functions and inverse trigonometric functions in details, but they are also continuous functions. Maybe I will talk about them in one of the next classes. Exponential functions. I hope you still remember the graph of the exponential function. 2 to the power x, e to the power x, things like that. Then logarithmic function. The domain of logarithmic function is set of all positive integers, and you see when the graph of the log function is unbroken. You can draw the graph without lifting the pencil. So that means it must be a continuous function. The same is true for the exponential function. You can draw the graph without lifting the pencil. Then, so these are, so almost all the functions that we know are nice functions, continuous. And we see these undesirable behaviors or discontinuities in these undefined points that are not in the domain, but somewhere in the middle of the middle, for example, in the one for the 1 over x, undefined point is 0, but it is surrounded by points in the domain of 1 over x. Properties of continuous functions. So say you have two continuous functions. So that means both f and g share a common domain, and at least both of them are continuous at a point C. So in that case, their summation, you can add the functions and make a new function. So that summation is also continuous. Differences, product, quotient, as long as the limit of the denominator is non-zero. Composition, scalar multiples, all these are continuous functions. Then imagine a function defined on an interval. Interval like this, bounded closed interval, to let's say real numbers. So this is the domain. I hope you remember this notation. This is the domain, and this is the range. This boldface are real numbers. So that means we can think of AB as an interval on the real line. For every point in this interval, we have a value. And so we can draw the graph of this function. This is what happened at P. And at this height is f of A. Look at the endpoints. Both A and B are in the domain too. Because since we are talking about the closed interval, closed means it includes endpoints. But this would be different for AB. If the function is defined on the open interval, that does not include endpoints. So we'll see two holes. Okay, this is what happened for a function defined on an open interval. We don't have values, y values assigned for endpoints, but when the function is defined on a bound closed interval, we have values at endpoints. So in the second case, we can talk about continuity at any point in the middle. So if I take some point in the middle, we can say, we can look at the left limit, right limit of the function at that point, and if those two values are equal to the function value at that point, we can say it is continuous at C. Now, let's think about an endpoint. Let's think about the point A. Now, to approach the point A, we don't have two different ways. We can only approach to A from the right hand side. So, the same is true for B. The only way to approach point B is from left hand side. So at point A and B, we cannot talk about the left limit and right limit because they are endpoints. Because since they are endpoints, we have only one way to approach them. So when you talk about a function defined on an open interval or bounded closed interval, we have to be careful. A function f is continuous on an open interval AB if it is continuous at each point in AB open interval. No mention about the endpoints. But still, if you want, you can ask for the left and right limits of f at a and b, because even though they are not in the domain, they are endpoints. You cannot ask, you cannot compute, or you cannot evaluate the function at either a or b because they are not in the domain, but still you can compute the limits. For a bounded closed interval, for a bounded closed interval a b, we can ask for the, we can evaluate the function at a and function at b, and also we can compute the right limit at a and left limit at b. So if the right limit equals f of a, we say f is continuous at a from the right hand side. Sometimes, in short, we say f is right continuous at a. Likewise, we can say f is left continuous at b if the function value b equals to the left limit of f at b. So, hmm, if f is not right continuous at a, the graph would be something like this. This is f of a, but this is what you get as x approach to a from the right hand side. If these two are different, you will have a pole again at the at the center. So if these two numbers are different, we'll have something like this. So f is not right continuous at a. So according to the graph is unbroken in the middle. Therefore, it will be continuous everywhere except at A. At A, it is not right continuous. So that is how the picture looks like. So that is about one-sided continuity. Like the one-sided limit, you can talk about one-sided continuity. So to test the continuity of a function, sometimes we don't need to look at all the points. We need to look at some particular points. Things like endpoints of the domain and some suspicious points in the middle of the domain. So let's look at this. The suspicious point is a number c where either the defining rule for the function changes or substitution x equals c causes division by c. So this particularly happens for piecewise functions, functions involving absolute value, and for rational functions. So let's look at this example. So in this example, we have a piecewise linear function. Function is piecewise because on different domains it has different rules. So from -5 to 2, the defining rule is 3 minus 6. That includes -5 but not 2. Then from 2 to 5, the defining rule is x minus 2. The second definition includes 2, but not 5. So if you think about the domain of this function, that the first interval includes everything from -5 to 2, but not 2. Then the second part includes 2 and everything about 2 up to 5, but not 5. So when you combine those two, the common domain, the domain of this function, is from -5 to 5, including -5, but excluding 5. The defining rule changes at x equal 2. Okay? Both pieces are linear functions. Linear functions are in particular polynomial functions. Therefore, both functions are actually continuous, except at the point where they meet. When they meet, these two line segments may have different left and right limits. There may be, if they do not meet exactly at a single point, then we have a problem. So let's see. So we have f of x equals -5 to 2, then 2 to 5, 3 minus 6, and x minus 2. So the first definition is valid from -5 to 2. Then the second definition is valid from 2 to 5. Okay? Now, let's see. We can think what happened as x goes to -5 from the right hand side. When x goes to -5 from the right hand side, we are uh, we look at what happens to the function near 5 from the right hand side. So if you take a point very close to -5 in the right hand side, at that point function value is 3 minus x. So 3 minus x. And you can see you substitute -5 into this formula, and that would give you the answer. If it is very close to minus, so at -5 it is supposed to be then 3 minus -5. And this is exactly what happened. This linear function behaves very nicely. We would have a problem with the rational function, but for a linear function or polynomial function in that manner, works in a very nice way. Then let's see. So that one is actually not a suspicious point, but anyway, we took it and what happens at that point. Now let's look at 2. 2 is a very suspicious point because in the left hand side we have a different definition, and in the right hand side we have a completely different way of defining it. So there is a very good chance that these two numbers are different. Let's compute what happened at 2. So let's go to 2 from the right hand side. So take a point near 2 but bigger than 2 because we are looking at the right limit. So to the right of 2, function is defined by this rule, x minus 2. So when you substitute 2, what do you get? So what do you get? You get 2 minus 2. Function limit is 0. In the same way, we can look at what happens when we go to 2 from the left-hand side. Take a point close to 2, but to the left-hand side. So in the left-hand side, function is defined by this rule, 3 minus x. And 3 minus x, when you substitute 2 into this formula, we get 3 minus 2, which is 1. Left limit and right limit are different. So because of that, the two-sided limit, we cannot say the two-sided limit has a meaning. So the two-sided limit does not exist. So there is a no comma limit, but left and right limits are different. So definitely f is not continuous at x equals 2. So 2 was a very suspicious point. And we found indeed that at that point the function is not continuous. By the way, function has a value at 2. If you want to compute f of 2, we need to go to the definition. On the first part includes everything from minus 5 to 2, but not 2. So the function, we cannot evaluate the function at 2 using the first formula. Then for the second formula, you see, here we have 2 less than or equals x. So that means this domain, the second domain includes 2. So to evaluate the function at 2, you need to use the second definition. So f of 2 is what happened. You take x minus 2 and set x equals 2. So the value is 2. 0. f of 2 is 0. f of 2 is 0. It equals to the right limit, but it is different from the left limit. So here we have a problem. At last, if you want, you can compute the left limit at 5, but the function has no value at 5. So if you want, you can compute what happens when we go to 5 from the left-hand side. So take a point close to 5, but to the left-hand side. And for that, we can use this purple color formula, x minus 2. So when you set x equal 5 in this formula, 5 minus 2 is 3. So as you approach to 5 from the left-hand side, you will get 3. So the graph of this function, let me rewrite it here. So 3 minus x from minus 5 to 2, then x minus 2 from 2 to 5. The graph of this function So from -5 to 2, we have a line with slope -1. Therefore, since the slope is -1, the angle between line and the positive x-axis is an obtuse angle, something bigger than 90. As we approach to 5 from the left hand side, sorry, as we approach to 2 from the left hand side, function value is 1. And slope of the line is -1, y-intercept is 3. So this is -5, 8. This point here is 2, 1. Then for the other part, right limit of f at 2 is 0. Uh, so the function, it would start here. So now let me erase this. And at 5, left limit at 5 is 3. But the function is undefined at that point, at 5. So the graph looks something like this. So 5, 3. This is 2, 1. The point over here is 2, 0. This is how the graph of this function looks like. And you see there's a clear discontinuity at 2 because left limit and right limit are different. Therefore, there is a jump discontinuity. And at 2, we cannot say the function is left continuous because the left limit exists, but the function is undefined. So if you redefine the function including 2, including 5, and assign 3 at 5, that would have continuous at 5. Left continuous. Likewise, at -5, we can say definitely function is right continuous. When you approach to 5, -5 from the right hand side, right limit agrees with the function value at -5. Therefore, it is right continuous. So we see a nice colored ball here, but on the other hand, at 5 we have a hole. So yeah, somebody was curious about slope. So this is 3 minus 6. As a line, slope is -5, -1, then y-intercept is 3. And for the other line, 2 x minus 2. Slope is 1, y-intercept is -2. That means that 0 y value is 3. If you extend this purple color line, it would hit the y-axis at -2. Yeah, we know everything about lines. Right? The example is not that complicated, but it is very illustrative. It tells us what can go wrong. So we took this function uh, and looked at what happened at the suspicious points, points where the defining rules changes. Those are called suspicious because at those points things can go bad. But for points in the middle of the domain, if the function is a familiar function like a power function or a polynomial or a rational function, exponential function, uh, usually we get continuous functions. Something really important about continuous function is called the intermediate value theorem. So this is very intuitive. Uh, the formulation looks a little bit complicated, but look at the picture. Suppose you have a function uh, defined on a bounded closed interval a and b. Hmm? And say you have, so at a, the function value is f of a, something like this. Hmm? At b, function value is f of b. So you have f of a and f of b. F of a can be larger than f of b, or f of b can be larger than f of a. We don't know. In general, those are two different numbers. Now, take any number between f of a and f of b. Let's call it L. Now, take L and draw a horizontal line through L. And if the function is a continuous function, the graph goes something like this. It can be any curve joining this point and this point. No matter what curve you draw, it will means the horizontal line through L. It will meet the horizontal line at some point. Maybe more than once, maybe just once. So anyway, at the intersection point, we can observe the x value. It's called that x value c. So if you substitute c into the function, f of c equals L. That is the idea. So for any L between f of a and f of b, there is a number c between a and b, so that f of c equals L. So for any value between f of a and f of b, there is a number on the x-axis whose evaluation at uh, whose evaluation uh, who gives f who substituted the function gives L. So this is called the intermediate value theorem. Let me give you a real world example. Suppose a girl is 5 feet tall and on her 13th birthday, and 5.5 on her 14th birthday. So I can say height of the girl is a function of time. And every time we can measure her height. So um, height is a function of time t according to the given information. On her 13th birthday, she is 5 feet tall, and her 14th birthday, she is 5.5. And we know height is a continuous function. It is not like you're 5 feet tall today, and all of a sudden, in next minute, you're 6.1 tall. It is not like that. Height is a continuous function. It changes continuously. So if I choose 5.2, there should be a day in between her 13th birthday and 14th birthday. There should be a day on which her height is 5.2. So height of this girl uh, on this day is 5.2. That is the idea. We don't know the day, we just know there is something. There is some day. So for any height between 5 and 5.5, there must have been a time t when her height was exactly h. Take any number between those two. We don't know about the other numbers. We cannot say there is a day on which her height is 6 feet. Maybe her maximum height is 5.5. I don't know. So we know for every number between 5 and 5.5, there should have been a day. But other than that, we cannot say anything like that. If a birth height is, let's say, 1.5 feet or something like that, then she must have assumed all the values between 1.5 and 5.5 from her birth to 14th birthday. That much we can say, but outside of that range is not our concern. We cannot say anything. So what is the use of this theorem? This is called the intermediate value theorem because it tells us uh, for between the value function should have assumed all the values between f of a and f of b. It must have assumed all these intermediate values. So that is why we call it the intermediate value theorem. Intermediate is useful because sometimes it helps us to solve equations. So how we talked about simple linear equations, quadratic equations, exponential equations, equations involving absolute values, square roots, all these simple types. But outside of those, there are hundreds of thousands of other equations that we cannot solve. For example, what can we say about the equation x squared plus 1 equals 2 to the power x. If you substitute some numbers, you can say x equals 0 is a solution. But if I change this to something like 5, then you probably we cannot solve this equation. There is no way we can solve this equation using something like a quadratic formula. The only thing we can draw is we can draw their graphs. And see looks like this. The parabola looks something like this. So there must be an intersection point here. So when they meet at the intersection point, we must have a solution. So there must be a solution, but we cannot say the exact value. Now we can use the intermediate value theorem to locate a solution. So here is what I'll do. I will take this function. So this is a continuous function, constant function is continuous, exponential function is continuous. So their summation. This is a continuous function. So this is the domain is set of all real numbers. So on any real number. Now let's see what f of 0 is 5 minus 1 equals 4. We can say f of 1. 1 plus 5 minus 2. So 6 minus yeah, 6 minus 2 is again 4. F of 2. 4 plus 5 minus 4 is 5. Let's see. F of 1 plus 5 minus 8. F of 4. 16 minus 5 minus 16. 2 to the power 4 is 16, so 5. Let's see again, f of 5. 25 minus 5. Sorry. No. I made a mistake here, I think. Yeah, this is plus. Plus 5 minus 32. So minus 2. Minus 2 here. Now, what does that mean? So we have a continuous function. At 4, the function value is 5. At 5, the function value is -2. And we know the graph is a continuous function, so it should go something like this. So somewhere in between 2 and, so somewhere between 4 and 5, it should have crossed the x-axis. So at this point, y value is c. So there is some c value between 4 and 5 such that f of c equals 0. What is f of c? This is c squared plus 5 minus 2 to the power c. So c squared plus 5 equals 2 to the power c for some c value in the open interval 4, 5. It is not 4, not 5, some number between 4 and 5. So, this equation, 2 to the power, sorry, x squared plus 5 equals 2 to the power x. In general, we don't have a method for solving this equation, but using the intermediate value theorem, we can say there is a solution for this equation between 4 and 5. Now, what you do is you make some guesses, trial and error. You can take the middle point, 4.5. And likewise, by substituting numbers, you can approximate this solution. You can write a computer program and do this. And even modern computers and modern calculators use this approach to solve these kind of unsolvable equations. Not unsolvable, but difficult difficult equations to solve using elementary methods. So this is called the root location theorem. If f of a and f of b have opposite algebraic signs, then there must be a c value between a and b such that f of c equals 0. So this helps us to find roots of equations, solutions of equations. Yeah, here is an example. Show that this has a solution in the interval 1, 4. You basically substitute 1 and 4 and observe that they have different algebraic signs. If at 1 function is negative, at 4 function is positive, so there at somewhere between 1 and 4, the graph of this function must have crossed the x-axis. So in this way, we can find an interval containing the root of this equation. Yeah, you see, there are plenty of other examples. But let's stop here and move to our next section. So the root location theorem is one of the important applications of continuity. There are other applications. If you want to have a glass of water or something like that, then this is a good time. Our next topic is a new chapter. It's called differentiation. This is the most important part of this course. Um, in the first chapter, we spent a lot of time making the ground, revisiting the concept that we knew. Then, in the second chapter, we talked about limits and continuity. Mm, Differentiation is one of the main important, main topics of calculus. So let me give you a motivation for this talk. So think about velocity time graphs that you learned in physics. So think about some object moving in the space at any point. So at the very beginning, you can say time equals 0. At somewhere in the middle of the path, you can measure its, let's say, time equals t, and velocity is v. Then you can draw the velocity time graph. Let's say initial velocity is v naught, then velocity is negative if the object change its direction. So according to this, the graph, the object must have taken path like this. At this point, it changes its orientation and come backward, something like this. Some object moving in this way. Now, can somebody tell me uh, how can we measure the acceleration of this object? Let's say at this point, let's say we want to measure the acceleration. How can we measure the acceleration of this? So how do you measure the acceleration of an object? Uh, yeah, very good. I put some answers. Gradient of the graph. Somebody suggests to use equations for the motion. Like v equal ut plus 18, and somebody suggests to use slope. Very good. If we had a piecewise linear graph as the velocity, we had something like this. So at each piece, we can say measure the slope of the graph. Slope of the graph is acceleration. So for this part, so So here we have three pieces. For the first piece, slope is constant. So the acceleration is constant. Acceleration is given by the slope of this line. And for the second line, the second line segment, again, slope is constant, therefore it has a constant acceleration. And we can see slope is negative, therefore it must be decelerating, decreasing its velocity. So again, from T2 to T3, it is still on a deceleration, but rate has decreased. So likewise, we can measure the slope. But when you have a nonlinear graph, like a curve, what can we do? So here, if you want to measure the acceleration at this point, this is not a line, this is a curve. So what you can do is you can think of the break, uh, the line that approximates the graph at this point. That means the tangent line to the graph at this point. The line touching the graph at this point. So this is the tangent. At T comma V. So this is, let's say this T. So slope of this line is the acceleration of the object at this point. So slope of the, this is, now we have a meaning for that. We have a way of computing this. So all we need is how to compute this. We know if we know the tangent slope of the tangent line, then we can compute the acceleration. But how can we compute the tangent line? In geometry class, in your grade 11 geometry class, you talk about tangents to circles and things like that. But in general, the graphs of these functions can be anything. They could be parabolas, they could be like hyperbolas, they could be anything. So how can we compute the slope of the tangent line? So this question puzzled people like Newton um, and other people around the same time. So they came up with a really good way of computing the slope of the tangent line. This is what we learn as differentiation, the method of computing slopes of tangent lines. So introduction to derivatives. Given a curve at a point, we can think of multiple lines going through the point. There can be points going through the lines touching the curve at that point. When the line touches the curve at a point, we call it the tangent line at P. The tangent line to a curve at the point P is the line that just touched the curve at P. If you think about the tangent line at P, for this particular graph, that line intersects the graph at another point R. At R, it is not a tangent line anymore. It is just line intersecting the curve. We can call it a secant line. And again, at Q, we have this tangent line. So a line joining given 2 points near another point. A line joining the given point P to a neighboring point of R on the curve is called the secant line. Secant lines, tangent lines. Now, with the slope of the tangent line. So let's see. I see somebody else is also drawing on the writing pad. Can you erase this? So let's say you have a graph of a function f of x, and you want to draw, you want to know about the tangent line at a point P. Let's say at x, at P, x coordinate is x, and y coordinate is f of x. So we want to know a line, know about the tangent line at this point. We know a point on the line, and we know it is tangent to the curve. But to compute the slope at a point, the slope of a line, we need two things. It is not enough to know a single point. We need at least 2 points. So without knowing another point, we have a problem. So how can we compute that? So what we can do is, the Newton and Leibniz came up with this really genius idea. Just give me a second. So what they did was, instead of taking a single point, they took the curve. Let's say they want to know the tangent point at this point, tangent line at this point. Let's say x, f of x. They took a neighboring point on the curve. Okay, let's say this point over here. It is very close to x. Okay, since it is very close to x, you can say x point, x coordinate is x plus some h for a very small h. Then the function value is f evaluated at that point, x plus h. Now, they have 2 points, and they can draw the line passes through both points. Line that goes through both points. This is not a tangent line, this is a secant line. But it is very close to the tangent line at this point, at point P. Hmm? Um, it is very close to this tangent line. Now you can compute the slope of the secant line. The slope of the secant line. This is y coordinate difference divided by x coordinate difference. F of x plus h minus f of x divided by h. Now we have a secant line, slope of the secant line. How can we make this to the tangent line? To make the tangent line, we cannot have two distinct lines on the curve. We only need one curve, one point. So what you can do is take this other point. Let's call it P prime. We need to move that point towards the other point. When you do so, what will happen is, so you have this secant line, and you are taking this point and moving it towards the other point. Then we'll have some other secant line over here, some other secant line over here, and when it is very really small, you'll get exactly the tangent line to the curve at that point. So what you really need is you need to decrease h value. So you need to decrease it and until this point coincides with P. So you need to move P prime to P. So what you really need is to let h goes to 0. So as h goes to 0, secant line goes to the tangent line. So slope of the secant line will go to slope of the tangent line. So slope of the tangent line is h goes to 0. It is a limit. So h goes to 0. We have an expression for the slope of the secant line. It is f of x plus h minus f of x divided by h. This looks a little bit complicated, but anyway, this gives us a way to compute the slope of the tangent line. Let me repeat what I did before. So first of all, we take a point, some arbitrary point x and x comma f of x. Then we take another neighboring point on the curve, a point close to x. Let's say x plus h. If h is a positive number, then the x plus h would be in the right hand side of h. If h is a negative number, x plus h would be in the left hand side. So we don't know. H is a very small number. That is what we don't know the sign. It can be positive or it can be negative. So we just take something very really close to x. And the y value corresponding to this x coordinate is f plus x, f of x plus h. So since you have 2 points, you can draw the secant line to through those 2 points, and you can compute the slope of the secant line. As h goes to 0, this x plus h point would approach to x. And when it moves, think about this. Now look at this animation. I hope you can see it. Look at the top graph. You take a neighboring point and draw the secant line, and as you move this new additional chosen point towards the other point, secant line becomes the tangent line. So secant line becomes the tangent line as h goes to 0. So slope of the tangent line, you can compute it as a limit of slope of the limit of slope of the secant line. So let's look at an example. Let's say we want to find the slope of the tangent line to the graph y equal x square at point -1, 1. So how do we do it? So our function is f of x equals x squared. We want the tangent line to this at point -1, 1. Y equal x squared is a parabola. So we are supposed to look at this point -1, 1. Take a point close to it. Uh, let's say the x coordinate is -1 plus h, a nearby point. Then the corresponding y value is -1 plus h squared. So now we should think about the slope of the line going through these 2 points. Slope of the secant line. Y coordinate difference. So -1 plus h square -1 divided by x coordinate difference -1 plus h minus the corresponding x coordinate is -1. So you can simplify this. Denominator is yeah, h. So this is m sec. Then slope of the tangent line. We get the tangent line when h goes to 0. So at point -1, comma 1. So here current x value, we took a neighboring point. That is what we did. The way we construct the tangent line is we take a secant line and let h goes to 0. Let the secant line become the tangent line. So x, the nearby point for x would be something like -1 plus h. So these two are very close if h is very small. So the equation for the curve is y equal x square. So every time if you know the exact coordinate, you square it to compute the y coordinate. So for this particular x coordinate, y coordinate, corresponding y coordinate is -1 plus h square. So h goes, slope of the tangent line is now h goes to 0, h minus 1 square minus 1 divided by h. Now this is a limit problem. Nothing complicated happens here, just a limit problem. So you want to evaluate the value of this expression as h goes to 0. So take a pencil and paper and evaluate this limit. So the first step to evaluate any limit is directly substitute the given value. Let's substitute h equals 0. When you say h equals 0, the numerator you get -1 square is 1 minus 1 divided by 0. That is something like 0 divided by 0. This is really bad. 0 divided by 0. This cannot be an answer to any problem. So there must be a solution. This is a rational function of h. So simplify it. So first step would be expand the square. H square minus 2h plus 1 minus 1 divided by h. We have a cancellation. 1 cancel with -1. Then what we have is h square minus 2h divided by h. Again, we have h in common for both terms in top. So let's factor h. So you can see immediately see a cancellation. H is in both numerator and denominator. So finally, what we have is h goes to 0, h minus 2. Now this is a linear function of h, so you should be able to simply substitute h equals 0. No rational functions or anything like that. So when you set h equals 0, the answer is -2. So slope of the tangent line at this point is 2, -2. If you look at the shape of the tangent line, it must be a negative number. You see, it looks something like this. So the angle between positive x-axis and this line is an obtuse angle. So slope must be a negative number, and this computation confirms our observation. So uh, tangent line to the graph at point -1, comma 1 has slope -2. So if you want, now you can use the point slope form to write down the exact equation of the tangent line. Remember, point slope form says if x naught and y naught are on the graph, and if m is the slope, this is how the equation looks like. So y minus 1 equals -2 times x minus -1. Y equals -2 x minus 1. So this is the equation of the tangent line. To y equal x square at -1, comma 1. At different points, we have different tangent lines. But this is equation of the tangent line to this curve at -1, comma 1. So, yeah, we have a way of computing tangent lines now. So this way of computing tangent lines is applicable to not only y equal x square, you can apply it to y equal x cubed and all the other functions. You compute slope of the secant line and let h goes to 0. When h goes to 0, secant line becomes the tangent line. So limit of this expression becomes slope of the tangent line. Right? So this is exactly what you have in the notes too. Slope of the tangent line. It's h goes to 0, f of x plus h minus f of x divide h. For this function, f is square function, f of x equals x square. And at this particular point, x equals -1. So you substitute everything you know, simplify and evaluate the limit. This limit of this expression is called the derivative of the function f of x. This derivative, what this limit compute is slope of the tangent line, but instead of calling it slope of the tangent line, we give it a name, derivative. This limit is the derivative. And we have a notation for that. So we have a notation for this. We use dy over dx. Difference of y coordinates divided by difference of x coordinate evaluated at -1. So this is how we write it. So this is the derivative of y equals x squared and x equals -1. This is how you read it. Hmm? So computing derivatives is not that hard. It is a limiting process. You compute a certain limit and that gives you the derivative. Do you want me to compute another limit? Do you want to see another computation of a derivative? So very good. Now let me take the same function. Hmm. Let me take the same function. Y we computed the slope of the tangent line at -1. I can compute it at some point like 1 comma 1 or 2 comma 4 or any other point. But instead of computing it at some other specific point, let me take a random point. Let's see, x comma x square. At point x, y coordinate is x square, right? So let me take this random point and compute the slope of the tangent line at this random point. So slope of the secant line would be f of x plus h minus f of x divided by h, right? Y coordinate difference divided by x coordinate difference. So this is x plus h square minus x square divided by h. Hmm? Now, slope of the tangent line is h goes to 0, x plus h square minus x square divided by h. So in this expression, you have two variables. X is a variable and h is a variable. And as far as this limit concerns, h goes to 0. So for this limiting process, h is the variable, not the x. So in the limiting, in the in this computation of limits, we say h goes to 0. We don't worry about x. For this computation, x is like a constant. It doesn't change. It will be there, but you don't need to worry about it. We need to focus on h. So how can we solve this? First step is again set h equals 0, and what happens? When you set h equals 0, you get x plus 0 square minus x square, so that is 0. Again, in the numerator, it is 0. So, something meaningless. Some undefined expression. So let's compute the limit. Let's simplify this and see what we can get. So again, you can expand x square plus 2xh plus h square minus x square divided by h. Let's see. This x square cancel with minus x square. Then h goes to 0. In the numerator, we have 2xh plus h square, and h is common. 2x plus h divided by h. They cancel each other. Then h goes to 0. 2x plus h. 2x plus h. This is a linear function of h. As I said before, x is like a constant for us. We don't worry about x. We just keep it there and simplify if we can simplify it. But our main focus is on h. Now, as h goes to 0, at this level, we don't have any problem for substituting h equals 0. So, set h equals 0, the answer is just 2x. So, slope of the tangent line at this point, this arbitrary point, just 2x. For example, at this point, our x is -1. So, slope of the tangent line is 2 times the x-coordinate. 2 times the x-coordinate. X-coordinate is -1. So, 2 times the x-coordinate must be -2, -2. So, we saw that. So, likewise, so slope of the at x comma f of x is, our notation is dy over dx, o f dash x. This is 2x. If the function is x squared, and at any point the slope of the tangent is 2x. So this gives us all the tangent lines and their slopes. So at -1 and 1, slope of the tangent line is 2 times the x-coordinate. And let's say toward the tangent line at x equals 1/2 and y equals 1/4. So slope of the tangent line at that point is 2 times the x coordinate, which is 1. Let's say you want the tangent line at 3, comma 9. Slope of the tangent line at that point, double the y coordinate, double the x coordinate, 6. So likewise, now you know not only a single tangent line, using this formula, you can compute slopes of all possible tangent lines. So this is what we call the derivative. So for the function y equal x square, we computed the slope at any point. Any slope of the tangent line is just 2x. So for the derivative of f of x equal x square, we got 2x. 2x is another function. So differentiation is process of converting a given function to another function. We were given x square, we computed the slope of the tangent line at any point, it is 2x. So derivative of x square is 2x, another function. So the process of taking the derivative, process of converting a given function to another function, this other function is the slope of the tangent is called the differentiation. Right, and this is good enough for today. Please go through the second example before next class. So starting from next class, we start talking about computing derivatives. So computing derivative is a limit process. Uh, you can give like think of any polynomial function or any rational function and ask for the derivative. And in C, this derivative is useful uh, for many things. Right. So yeah, this is the time for questions. Do you have any questions for me? What questions do you have? Yeah, as I said before, I will post an assignment for you at some point of this week, and I will inform you. Uh, I will email it to you as well as I post it on the LMS page. Because I got to know that some people still don't have the access to LMS. So please get your registration done as um, quickly as you can. Um, so uh, I should have your email Yeah, that's a problem because I usually get the email list through the LMS. If you don't have access to the LMS, then that means your email is not there. Hmm. So what I can do is I can email it to everybody in my email list, and you have this WhatsApp thing. So please share your assignment on the WhatsApp. Hmm? And also, please share my notes in the WhatsApp group. In that way, the other people can also get it. Hmm? Thank you, Kimhani, for your message. Hmm? All right. So it seems like we don't have questions about the material that we discussed. So I will close the Zoom meeting now. If you have any question, you can email me in the meantime. Okay, good luck. Enjoy the rest of this week. Uh-huh. Um, so usually for an assignment, I'll give you a week. Uh, so a week from the time I post it. I'll write it down on the assignment. On top of the assignment, I'll give you some instructions. Hmm? All right. Have a nice day.